glad to introduce David Berger from Dresden. He was going about Liouville and strong Liouville properties. Please.
Thank you very much for the introduction, and thank you for the organizers to let me speak here. I will speak about the Liouville and strong Liouville properties of generators of Levy processes. And at the start, I will give the definition of the Liouville property and also define what is a Levy process and characterize the generators. After that, I will give the main result and give two different proofs. First one is more analytic, and the second one is more stochastic if you want. After that, I will give some direct consequences and discuss shortly the strong Liouville property. Okay, the Liouville property for the Laplacian. The Laplacian is just the sum of the second derivatives, and we say that the Laplacian enjoys the Liouville property if for every f and L infinity are bounded, such that the integral of f times the Laplacian of phi is equal to 0 for all phi in the space of infinitely differentiable functions with compact support implies that f is constant. It is well known that the Laplacian satisfies this property. You can find it, for example, in the books of Remander. But we are not interested in the Laplacian, we are more interested in more general operators, and we study the generators of Levy processes. A Levy process is a stochastic process which is starting in 0 and has independent and stationary increments and right continuous paths with finite left-hand limits, also called Cutlock process. Examples for a Levy process are a Brownian motion or an alpha-stable process. And we will see that the generator of a Brownian motion is the Laplacian, and for the alpha-stable process, we obtain the fractional Laplace. Okay. But now we discuss the generators of a Levy process. The generator psi of the Levy process is a pseudo-differential operator. So what does we mean with that? Take u in the space in this Schwarz space, a perfectly decreasing smooth function. Then the Fourier transform of L psi of u is equal to minus psi xi times the Fourier transform of u, where psi is our symbol, and the symbol of our operator is given by this nice form, where B is an Rn, Q is a matrix of dimension n, positive semi-definite, and nu is a radon measure on Rn without 0, such that the minimum of x squared and 1 is integrable with respect to nu. Especially a triplet BQ nu uniquely determines psi, and we call psi the characteristic exponent of xt. This comes from the fact that if you take the characteristic function of xt at point z, then it is given by e to the power of minus t psi z, and therefore it's the characteristic exponent. Our main results states the following: that L psi be a generator of a Levy process with characteristic exponent psi. The operator L psi has the Liouville property, which means that if f is an L infinity and for all phi in the space of infinity differentiable functions with compact support, the integral of f times the adjoint operator applied on psi out and phi is equal to 0, implies that f is constant, if and only if the zero set of the characteristic exponent satisfies this condition, so the zero set of the symbol is equal to 0. Now, if you think about it, if you look at the Brownian motion, then the symbol is given by the norm of z squared, and it is easy to see that the zero set is just equal to 0. Okay. Now, we always mentioned that the function f needs to be in L infinity, but we can just relax this condition. We can always assume that f is in C infinity, where all derivatives are bounded. How to see that? You take just a Friedrich modifier, j epsilon, and take the convolution of the Friedrich modifier and f, and we obtain that this solves again the equation. And especially if you take the limit, so you take the limit, you obtain that j epsilon convoluted with f converges to f in some sense, and if j epsilon convoluted with f is constant, then f needs also to be constant. Okay. So our first proof is more analytic. And let us mention first that the zero set of psi is a group or a closed subgroup of n. How to see that? Observe that if you take the symbol of the generator of a Liouville process, then the following estimates hold. The square root of the norm of psi plus eta is smaller or equal than the square root of the norm of psi xi plus the square root of the norm of psi eta. Which does it mean? You can say that if psi has only the trivial zero group, then this function defines also a distance function. And how to see that this is now a group? Just assume that psi xi is equal to 0 and psi eta is equal to 0. And you see that psi xi plus eta is smaller or equal than 0 in norm, so it's also 0. Now we know that as this is a closed subgroup, there exists a subspace of Rn and a closed discrete subgroup contained in the orthogonal subspace of E, such that the closed subgroup is just the direct sum of G and A. Okay. Now our proof works with pointwise multipliers, and for that we need to know that our symbol defines really a multiplier in the Schwartz space, and therefore let us mention if psi is in C infinity, then the Liouville measure has all finite moments, and if the Liouville measure has all finite moments, then psi is also in C infinity. So the finite moment implies especially that a Liouville process has also finite moments of all order. And in this case, all of the derivatives are also polynomial bounded, which we need later. Okay. Now we want to say the result. Let L psi be the generator of a Liouville process with characteristic exponent psi, and assume that psi is a C infinity function. So it is polynomial bounded and all derivatives are polynomial bounded. The operator L psi has the Liouville property if and only if the zero set of the symbol is trivial. How to show it? At first, we can assume that the zero set is a discrete group. Otherwise, we just take the projection onto this discrete group. Now, psi is a pointwise multiplier in the Schwartz space. So we have that 0 is equal to the integral of the inverse Fourier transform of f times the complex conjugate of psi times the Fourier transform of phi. This implies that the support of the inverse Fourier transform is contained in the zero set of the complex conjugate of psi, and especially the zero set of the complex conjugate of psi and the zero set of psi is equal. So we obtain that this is also contained in the zero set of psi. Now, by a classical result from distribution theory, you can find it in Traves, we obtain that fx is equal to the sum, fx is equal to some constant times the sum over all gamma in the zero set of psi of a constant which depends on gamma times e to the power of minus I gamma times x, where gamma times x is defined as the usual scalar product. Now, you can see if the zero set of psi is just 0, then f needs to be constant, and if the zero set is not trivial, then you can find easily a non-constant function f. So the result is already proven. Now, we needed the assumption that psi is in C infinity, but it is well known that you don't need it. The first result for the Liouville property for the generators of a Liouville process can be found in Liouville and others. They proved also the Liouville property, but stated the assumption in terms of the support of the characteristic triplet. We are stating it in form of the symbol. Okay. We are using now fixed point theory of convolution equations, especially the theorem of Choquet-Denis, which was first proven by Denis, especially. Take a probability measure mu on Rn and let h be a bounded and continuous function. if H is equal to H convoluted with mu, then the support of mu is a period of H. And especially, this is if and only if. So every point of the support of mu must be a period of H, then the convolution equation holds, otherwise not. Okay. But we are looking at L psi of f equal to 0, which is not a convolution equation, so we need to describe it in a different way. And therefore, let L psi be the generator of a Liouville process, and denote by Pt and R lambda the corresponding semigroup and resolvent family. Let f be a continuous and bounded function. Then the following assertions are equivalent. If L psi of f is equal to 0 weakly, then PTF is equal to f for all t, where PTF is just equal to the integral of f plus y integral with respect to mu t, where mu t is the probability measure of xt. So we see here that we have a convolution equation in the last line. So we can use the theory from Schottky. Okay. Now we can state our main result. Let L psi be the generator of a Liouville process of characteristic exponent psi. The operator L psi has a Liouville property if and only if the zero set of the characteristic exponent is trivial. So we don't need the assumption of psi anymore. Now assume that you have a non-constant solution f. Then we know that the points of periodicity is a closed subgroup of the additive group Rn. And by using Schottky nu, we obtain that all the supports of mu t are contained in the periodic points of f. Without any further assumptions, we can just assume that the periodicity points of f are equal to the integers to the power of n, which implies that mu t is for every t greater than 0 a non-trivial lattice distribution on Zn. Now, by using classical results from probability theory, we do not have found it, but we have proven it ourselves, and it's very natural in one dimension, and it's well known, that if you take the characteristic function at the point 2p times e1, e2, and en, then this needs to be equal to 1, where ej is just delta ij, where delta ij is equal to 0 if I is not equal to j, and 1 if I is equal to j. So, as the characteristic function of mu t is equal to e to the power of minus t psi xi, and t is arbitrary, we conclude that 2p times ej is in the zero set of psi for all j from 1 to n. Therefore, we conclude that it cannot be a trivial group. And the proof is already done, so it's a very fast proof. Examples. Now, what kind of symbols has the Liouville property and which does not have the Liouville property? If you take a symbol, the norm of z squared, then you see that the zero group is just simple 0, the trivial group. So the Laplacian has the Liouville property. And if you take a symbol, the norm of z to the power of alpha for alpha between 0 and 2, this has also the Liouville property. I think it is more interesting to know which symbols does not have the Liouville property, and we can describe it completely. If you take just one dimension, psi of z equal to the sum over all integers of ak times e to the power of ikz minus 1, then you see that 2 pi, if you take z equal to 2 pi, and this is equal to 0. So it does not have the Liouville property. And especially every one-dimensional symbol which does not have the Liouville property is exactly of this form. And by using a projection of the symbol, you can see that there always exists such a one-dimensional projection which has exactly this form if it does not have the Liouville property. Okay. So direct consequences. Assume that the Liouville process with characteristic function psi has a transition probability mu t such that for at least one t0, the measure mu t has a strictly positive density. In general, pt0 is always greater than 0 for all x. Then the generator L psi has the Liouville property. Okay, but you do not even need that it has a strictly positive density. But it's in this form, so I need it. Okay. Furthermore, if you take the generator of the Liouville process and assume that it has a Liouville property, then you know that all powers of L psi has also the Liouville property, and especially the power of L psi of every order has the Liouville property, then also L psi has the Liouville property. Okay. And now the strong Liouville property. Assume that L psi is the generator of a Liouville process with characteristic exponent psi with triplet BQ nu. Assume that there exists a locally bounded submultiplicative function g from n to the positive numbers, satisfying that the integral with respect to nu is finite. And then for every measurable positive and g bounded function, so f, which means that f is greater or equal than 0 and smaller or equal than g, the following assertions are equivalent. L psi of f is equal to 0 weakly implies that f is constant, and the zero set of psi on Rn is trivial, and the zero set of psi on I times Rn is also 0. You see that you need some kind of extension on the imaginary axis to have an unbounded non-constant solution. Okay. Thank you for your attention. I think I was way too fast.
Thank you for your talk. Are there questions?
Yes, there are several. So let us start from the main result. You have already presented some examples of symbols which correspond to processes with Liouville or no, without Liouville property. But nevertheless, looking at this Levy-Hinchen presentation, what can we say? So does it mean that compound Poisson processes do not have Liouville property? Taking into account your examples, or just Poisson process?
Just Poisson processes, basically. Or if you,
they do not have.
You need that that the support of nu is contained on the integers or some discrete group. So if you take, I mean, you can construct a compound Poisson process such that it holds, I believe. So I would say
that what?
It is necessary that if you take, wait a moment. Okay, here.
Yeah.
You can construct a compound Poisson process with exactly this
structure.
Symbol.
So you have a lattice.
Yeah, you need to be concentrated on a lattice, basically. And I think.
Yeah, so if you have just a Poisson process, you cannot state anything. Does it have a Liouville or not? You cannot state. So probably one can compensate drift with something non-local so that Liouville property is preserved or violated. Yeah, but just.
Yeah, exactly.
Yes. Okay. So then another. So my first, when I have just seen the statement, I thought that okay, Laplacian yes, fraction Laplacian yes, probably a symmetric alpha stable. Not alpha stable, symmetric Levy process. But symmetricity does not provide anything. No, it's not enough. Nothing to do with symmetric processes. Okay, and then the next question is, so you have said that if we have a Liouville property, then if we consider powers of a generator, then we still have a Liouville property. Yes? What about subordination? Not powers, but just composition with some Bernstein function.
We have something in the paper with me, so I believe if the subordinator and its Laplace transform has no 1 or the exponent has no zeros, then the Liouville property always holds, I believe, but I need to look it up.
Okay. Thanks. So these are my questions. And once again, why we need it at all? So why it is important property?
That is a very good question.
Okay, good. And another question that probably again, so looking at the formulation of this property, one could say that probably one can speak about this property for considering not just generators of Liouville processes, but all operators satisfying this positive maximum principle.
Yes, you can ask this question, but our proof will not work. We need constant coefficients because of the
So they're crucial, constant coefficients. Okay. Okay, thank you.
I mean, if I may also had to comment on the very last remark. So I think in this stage we have heard a bit about eventual positive semigroups. So we don't have precisely a positive maximum principle, but something very tightly related to the weakened version of it. So some realizations of bi-Laplacians are a good example for this. Do you know if this gives you an example of application of your theory?
Yeah, you can take the bi-Laplacian. It's just the square root of the Laplacian, so you can obtain.
No, it's not. That's the point. No, it's not, because I mean, depending on the boundary conditions. So, for instance, if an interval you take typically n Neumann, this is no power of the Laplacian, but it is eventually positive. I mean, it generates an eventually positive.
We have not considered bounded domains. We have only considered n. So.
So you have what to do in the future.
There's much more to do.
Yeah.
Okay, thank you.
Yeah, thank you. Yeah.
Okay, then,
best wishes to René Schilling.
Okay, if there are no further questions, then thanks to the speaker again. And the next talk will